Section 5.1, Angles and their measure. So first off, we have these things called trigonometric functions. Now we're not going to define them yet, but just to tell you what a trigonometric function is, a trigonometric function, sometimes called circular functions, are functions of an angle. That is, they're going to take an angle in and they're going to spit out something. They're going to be used to relate angles of a triangle to the lengths of the side of a triangle, and they're important in modeling of periodic phenomena and lots of other applications. But to get started, we have to set up some base terminology. So first we need to talk about these things called rays. So a ray is that portion of a line that starts at a point and then extends indefinitely in one direction. The starting point V of the ray is called its vertex. And so notice that a ray is just a dot and then a line that goes on for some amount of distance. If there's an arrow, it's an indefinite amount of distance, and that's a ray. Well, the deal is what we're going to do is we're going to fix a ray, and we're going to put it somewhere. And then we're going to rotate it. Well, this first ray that I draw is going to be called the initial side. Then I'm going to rotate, and I could rotate this way, and it's fixed to the vertex, and then wherever I stop is going to be what's called the terminal ray. So the initial ray is where we start, the terminal ray is where we end. And then this angle that is created is the angle. Now, the deal is that the direction that we rotate matters, and so if you rotate counterclockwise, we're going to say that that angle is positive, and if we rotate clockwise, we're going to say that that angle is negative. So notice for this first one, the initial side is this one, this bottom one, and then it rotates counterclockwise, so this is going to be a positive angle. This one, here we have the initial side is here, the initial ray, and then it rotates down to flip back around to get this side. So this is actually going to be a negative angle because we went in a clockwise rotation. Now there's no reason we can't pass the initial ray again if we want, so for this one, it starts with the initial ray here, and it rotates all the way around, passes itself, but it's going to be a positive angle where this is the terminal ray. Now often, we're going to use lowercase Greek letters to represent angle measurements, that is the amount of rotation. But we're not required to use those. We could use any symbol or letter to represent the angles, but usually Greek letters is what we use. Theta is common, so are alpha, beta, and gamma, just to make sure you're okay with those. Now, earlier, if you noticed, I drew my initial ray here and then rotated some amount and got to here. There's nothing wrong with doing that. It's still an angle. But in general, what's going to happen is we're going to work from what's called standard position. And so standard position says that we're going to superimpose our rays onto an xy coordinate plane. And so we're going to put our vertex at the origin, and then we're going to put the initial ray on the positive x-axis, and then you'll rotate from there. And we're always going to assume that we're in standard position unless someone tells us otherwise. And so that just means we'll start on the positive x-axis and then we might rotate positively, that is in the counterclockwise direction. Or we could start with that initial ray on the positive x-axis and rotate clockwise, and that would be a negative angle. Well, when we're rotating these angles from our standard position, the truth is one of two things is going to happen. If you do a rotation, and for the moment just assume we're doing counterclockwise rotations, if you do a rotation and you stop somewhere, then you're either going to be on an axis, xy axis, or you're going to be somewhere in the plane. Well, the deal is that if we land on an axis, we're going to call those quadrantial angles. And so anytime you land on an axis, it's quadrantial. And so notice that your quadrantial angles are the 0-degree angle, which is right here. That's the same place it starts. You just don't move the initial ray. Or you could rotate counterclockwise 90 degrees, and so you have a 90-degree rotation on the positive x-axis. That's a quadrantial angle. You could rotate from the standard position to the negative x-axis, and that's a 180-degree rotation. That's another quadrantial angle. Or you could rotate you could rotate positive 270 degrees, and you could end up on the negative y-axis, and that is the other quadrantial angle. Now technically it's true that you could also rotate all the way around and end up where you started. Now this is actually going to be something interesting, but notice that that quadrantial angle if you rotate it all the way around, ends up looking like the exact same thing as the 0-degree angle, except that it could also be 360-degree angles. This will be a thing that's relevant later, but we'll just leave it like that. Now notice my heading here, degrees on a unit circle. Now I want to talk about unit real quick. We're going to see this phrase, unit circle, often over and over and over again. But just to make sure you're aware, unit is just a word for one. That's all it means. Unit 1. Well, the deal is that when we say unit circle, what we actually mean is a circle with radius 1. And so anytime we hear unit circle, that automatically means you're dealing with a circle that has a radius of 1. Well, after that, then remember that with degrees, 360 degrees is going to be one complete counterclockwise revolution around a circle. That is, 1 degree is equivalent to 1/360th of a complete revolution. And if you were to think about 60 degrees, so that's the same thing as 60 over 360, or that's 1/6 of a complete revolution. And so a right angle is going to actually be, remember that's a 90-degree angle, that would be a quarter of a revolution counterclockwise, and like I said, is 90 degrees. A straight angle is going to be a half of a revolution counterclockwise, and that's going to be 180 degrees. So if nothing else, flip back and look here. There we are. If you rotate counterclockwise a quarter of the full revolution, 90-degree angle. A straight angle is this 180 degree. So now let's approximate the location of these angles and then identify which quadrant they're in. As a reminder, our quadrants are numbered 1, 2, 3, and 4. So because we're counterclockwise rotating, quadrants are 1, 2, 3, and 4, usually represented via Roman numerals. Well, also it may be useful to start getting into the habit of remembering where our main angles are. Well, here is 0 degrees. If I did a full rotation, this would also be 360 degrees, so that's helpful. Then a quarter of a rotation, that's going to be 90 degrees. Half of a rotation, that's going to be 180 degrees. And then 3/4 of a rotation, that's going to be 270 degrees. And then there we are, the 360. So where does 135 degrees live? Well, of course, we're always going to start from our standard position. So we're going to start from the positive x-axis, and then we're going to rotate. Well, if we rotate from the positive x-axis, we're going to end up somewhere over here. So I'm going to say that 135 degrees is somewhere over there. I may be off, it's not to scale, but we just need to know close to where it is. Well, that being a positive rotation means we had to go counterclockwise, and notice that we're in quadrant 2. Next one, here we have a negative 120 degree rotation. Well, first off, because it's negative, note that we start from our standard position, that is the positive x-axis, and we're going to rotate clockwise. Okay? Well, if we're rotating clockwise 120 degrees, we've got to be careful, because technically if we're doing negatives, this is again 0, but then this is actually negative 90 degrees. And then that makes this negative 180 degrees. And that makes this negative 270 degrees. And then this down here is going to be negative 360 degrees. Okay? Same idea that we had earlier, but because we're going in a negative direction, we're going in a clockwise direction, make sure you realize that the counting changes a little. So then, where does 120 degrees live? Well, it's got to be over here somewhere. So somewhere there. Once again, I make no claim that it's to scale, but it is in quadrant 3. And so we know now that this is in quadrant 3. Degrees, minutes, and seconds. Well, the truth is that sometimes the way we label things changes over time. Degrees, minutes, seconds are pretty useful, and they're often still used with maps or GPS coordinates. To connect this with something that you may be familiar with, 1 minute of latitude is going to be equal to 1 nautical mile. And so it could be very useful when considering charts or maps or GPS coordinates, because it actually gives you a measure of distance when you're talking about minutes. And so that could be helpful. Now, do note that a nautical mile is not the same as a land mile. When we say miles per hour, like in your car, that's not a nautical mile. But when you're talking about boat speed in knots or nautical miles per hour, then you are talking about these nautical miles. So, first off, in a full circle, there's of course 360 degrees in a full rotation. Well, then what's going to happen is to break it down to degrees, minutes, and seconds. Minutes lends you to this idea, how many minutes are an hour? 60. Well, that is, each degree is going to be split up into 60 parts. Each part's going to be called 1 minute. So 1 minute, denoted by 1 prime, we'll just read this as 1 minute, is 1/60th of a degree. So 60 minutes is going to make up 1 degree. 1 second, denoted by 1 double prime, is 1/60th of a minute, so 60 seconds is going to equal 1 minute. Well, then we need to be able to convert things. So how are we going to do this? Well, we just need to remember that there are 60 seconds for every 1 minute. There are 60 minutes for every 1 degree. Alright, how does that help us? Well, that means that this 45 degrees, 10 minutes, 15 seconds is really the same thing as going, oh, well, that's the same thing as 45 degrees, 10 minutes, but let's make 15 seconds into minutes. So let's just write it over 60. 15 over 60, now that's in minutes. Well, then you could actually find what is 15/60ths. Well, as a decimal, 15/60ths is just a quarter, or 0.25. And so that means that this is the same thing as 45 degrees, 10 minutes, and 0.25 minutes, or 0.25 minutes. Okay, then what can you do? Well, now that we have these minutes, we know that there's 10.25 minutes, but we also know that there are 60 minutes for every 1 degree. Just write that over 60 and put the degree symbol on it. So that's going to be 45 degrees, and 10.25 over 60 degrees. Technically, you're just adding those, but 10.25 divided by 60 in decimal form is 0.17083333 repeating. And so that's going to be 45.17083 repeating. But since we're rounding the answer to 4 decimal places, 3 does not affect the 8. And so this is our decimals degree form. Let's do it again. I have 34 degrees, 15 minutes, 27 seconds. Well, that's the same thing as 34 degrees, 15 minutes. 27 over 60 minutes. But then I'm using my calculator. 27/60ths is 0.45, which means that this is 34 degrees and 15.45 minutes. Then we just repeat to get rid of the minutes into degrees. 34 degrees, 15.45 over 60. Now that's in degrees. Find that decimal representation. 15.45 divided by 60 is 0.2575, which means that this is then 34.2575 degrees. Now we want to convert this to degrees, minutes, and seconds. Well, how can we do this? Well, first off, just break off the decimal. Kind of reverse what we did. Well, that's 12 degrees and 0.87 degrees. I'm just kind of breaking it up, thinking about this as a plus between. Well, but how can I get rid of the degrees and put it in terms of minutes? Well, all I need to do is think about this as 0.87 degrees. Remember that 1/60th of a degree is equal to 1 minute. If I could get 60 in the denominator, then I could just drop the 60 in the degree symbol and then it's in minutes. Well, how do I do that? You multiply top and bottom by 60. That's going to be 0.87 over 1 times 60 over 60. And then that's going to give me 52.2 over 60 degrees. But what do we say? We can drop the 60 in the degrees and then it's minutes. So this is the same thing as 52.2 minutes. Short, multiply by 60 on the decimal and you're good. So that's going to be 12 degrees and 52.2 minutes. Well, then all we need to do is worry about this decimal to get our seconds. And so break it off. That's going to be 12 degrees, 52 minutes, and then we've got to deal with this 0.2 minutes, but all you need to do is multiply it by 60. 0.2 times 60 is going to give us 12, and that's going to be in seconds. And so this is 12 degrees, 52 minutes, 12 seconds. Again, easy. 1 degree. Break off the decimal, 0.53 degrees. Just multiply 0.53 times 60. That's then going to be 1 degree and 31.8 minutes. Then break off the decimal again. So 1 degree, 31 minutes, 0.8 minutes. Multiply 0.8 by 60. And then you're going to get that this is 1 degree, 31 minutes, 48 seconds. Notice that we didn't have to round these, but that's not necessarily going to be the case in all examples. Another way to measure angular rotation is going to be this thing called radians. So radian measure, theta of an angle, is the measure of the ratio of length of the arc it spans on the circle to the length of the radius. What does that mean? That means that theta, if this is my rotational angle, and then this was my initial ray, and this was my terminal ray, S is the arc length subtended. And so all we have to say is that theta in radian measure is S divided by R. Now, this is kind of strange. You'll get used to it, and it's going to be necessary, so please don't ignore radians. Truth is radians are a unitless measure, and they're going to be preferred for most scientific applications. And so calculus or anything else, you will have to work in radians. The majority of this course will end up working in radians as well. But let's think about this for a moment. Let's pretend for one moment, because we don't have a frame of reference for how big a radian is. Well, let's think about this, and let's pretend for one moment we start right here, and we rotate the full rotation. All right. In degrees, how far did we travel? Well, we just traveled 360 degrees, right? Great. But let's do something a little strange. Let's pretend we're on this thing called the unit circle. Well, technically, notice that this picture is the unit circle, so R is going to be 1 in this situation. And so 1 being a full rotation and S being the arc length, well, if we do a full rotation, what's the arc length of a full rotation? The arc length of a full rotation is really going to be the circumference of a circle with radius 1. Well, remember, the circumference of a circle is 2 pi r. Well, since r here is 1, the circumference of this circle is 2 pi. Well, that means that one full rotation in radian measure is 2 pi radians. And so that's what I'm trying to tell you, is that anytime we're talking about radians, just like a full rotation in degrees is 360 degrees, a full rotation in radian measure is 2 pi. Now, if we use that definition of radian measure that we just gave, we can get what's called arc length. And so arc length is going to be S is equal to r theta. There are some restrictions here, and that is, for a circle of radius r, a central angle. What is a central angle? It's going to be a positive angle whose vertex is at the center of the circle. The vertex is here, and we're pretending we're in standard position, and so the rotation is counterclockwise, which is positive. That central angle of theta radians subtends an arc whose length S is equal to r theta by manipulating the previous definition of radians. Well, if we know now that S is equal to r theta, as long as theta is in radians, and S is arc length, and r is the radius of the circle, and we want to find the length of the arc of a circle of radius 4 meters subtended by a central angle of 0.5 radians, then all we need to do is calculate the arc length is equal to the radius r meters times the radian measure 0.5, which means that the arc length is going to be 2. half of 4 is 2, and our units are meters. Now, let's consider that we want to convert between degrees. Now let's consider that of course we want to be able to convert between degrees and radians. Well, if we want to convert between degrees and radians, let's try to remember how can we convert. I always remember that the circumference of a circle is equal to 2 pi radians, and we're usually talking about the unit circle, and so that's usually 1. Well, if the circumference is 2 pi radians in a full rotation, that's equal to 360 degrees. Then all we need to do is write that because it's 1. So 2 pi divided by 360 degrees is the same thing as pi over 180 degrees. And so that is pi radians divided by 180 degrees is the same thing as 180 degrees divided by pi radians. It's all equal to 1. This is the unit conversion factors that you're going to use, one of these two. You could use 2 pi over 360, but of course, or 360 over 2 pi, but of course these reduce to be the same thing, so it's fine. So, how do we convert between degrees and radians? Well, if we want to convert from degrees to radians, because you're just doing a unit deletion, think dimensional analysis if you've seen that before, then I just need degrees in the denominator, so pi divided by 180, that's the one that I multiply by, and whatever solution I get is the answer. And then it won't have a unit because it'll be in radians. If we're trying to convert from radians to degrees, well, you need to cancel radians. Radians are a unitless measure, but that still means radians need to be on bottom. And so you're going to just do this multiplication of 180 divided by pi, and whatever you get is your degree answer. So we're going to convert from each angle in degrees to radians, and we're going to do two things. We're going to express the answer in exact form, and we're going to round it to 2 decimal places. So 2 answers. Well, because we just need to convert this from degrees to radians, I know that my conversion factor is pi divided by 180 degrees. Degrees on bottom because I'm trying to cancel degrees, so multiply by pi over 180 degrees. And then the degree unit cancels, and we get 80 over 180 times pi. Pi, of course, could be out there to the side, or it can be on top, but it cannot be on bottom. Well, 80 divided by 180, that's going to reduce, and so this is really 4 pi ninths. That's the exact answer. If you want to express it in a rounded form, then we're going to have to approximate, and we're going to round it to 2 decimal places, but you're going to need a calculator. So make sure that you use the pi button. 4 times pi divided by 9 is equal to approximately 1. I get 396, which means that it's going to be 1.40. And this doesn't get a degree. If you wanted to write rad or radians for yourself, just to keep yourself on track, that's okay, but technically there's no unit there. Now we just repeat the same process. Negative 30 degrees times pi over 180. The degrees cancel. And then we're going to be left with negative 30 times pi divided by 180. Then we want to reduce the fraction. That reduces to 1/6. Make sure you remember that it is negative, so that's negative pi sixth, which, that's our exact form. Pi divided by 6 is going to be approximately negative 0.5. 2 decimal places, I get 0.523, so that's 0.52. 8 degrees, same process, multiply by pi over 180 degrees. The units degrees cancel, then this is going to be 8 pi divided by 180. Reduce as much as possible. That's going to be 2 pi 45ths. That's our exact solution. And then since we want an approximation, that's going to be 0.14. Now we're converting from radians to degrees. So just flip that conversion factor. Radians need to be on bottom, so that's pi on bottom, 180 on top. And so now we just multiply by that. That's going to be multiply by 180 degrees divided by pi. Notice that in this one, pi divided by pi is 1. Then we're going to have 3 times 180. That's negative 540 degrees divided by 5, which is negative 108 degrees. Make sure you pay attention to those negatives because it does matter. This is the exact form, there is no rounding, but if they said round it, you just retype the answer. Pi thirds times 180 degrees over pi. That's going to be equal to pi divided by pi is 1. 180 divided by 3 is 60. We get 60 degrees. That's our exact. And if they wanted you to round it, same answer. And then for 8 times 180 degrees divided by pi. So our exact answer here is going to be 1,440 divided by pi degrees. So technically the degree unit is on everything. That's the exact solution. But, of course, if we want an approximation, that's going to be approximately 458.37 degrees. Now, just to convert some more, I'm not going to do all these outright, but realize that just multiply each one of these by pi divided by 180 degrees. The degree units are going to go away, and then we're going to get the following radian measures. 0 degrees in radians is 0. 30 degrees in radians is pi sixth. 45 degrees in radians is pi fourths. 60 degrees in radians is pi thirds. 90 degrees in radians is pi halves. 180 degrees in radians is pi. 270 degrees in radians is 3 pi halves. 360 degrees is 2 pi radians. Now once again, it's okay in the beginning for you to use that conversion factor where we just multiply the degrees by pi divided by 180 degrees and then simplify it as much as you can. Realize that in the long run, you're going to want to know these relationships. And I've put these on here specifically because these are going to be what we call the important, or the ones that give us exact values, later. Not just these, but if you have these, you can get all the other ones, but this is where you need to make sure you can do those. Now, just to make sure we're okay with our rotations, assuming that we're in standard position, that is, we're starting on the positive x-axis and then positive counterclockwise rotations, this rotation would be pi sixths, the second one would be pi fourths, third one would be pi thirds, fourth one, well, that's a 90-degree rotation, so that's actually pi halves. Keep going. If you rotate a little bit more, how much is that going to be? Well, I'll go ahead and give you a heads up. This is actually a rotation of an additional 30 degrees, but that ends up being 2 pi thirds. And then if you rotate a little bit more, this is going to be 3 pi fourths. That's because going from this 90 degrees to here is a 45 degree additional rotation, or 135 degrees, which is going to equal 3 pi fourths. Then if you go a little bit more, that's going to be 90 degrees plus 60 degrees, or 5 pi sixths. And then if you start at 90 degrees and you rotate all the way around, that's 180 degrees, but we already know that that's pi. Then down here, you're going to rotate an additional 30 degrees, or pi sixths, and that's going to be 7 pi sixths. Rotate a little bit more to this one, that's going to be a rotation of 45 degrees, and that's going to be 5 pi fourths. From here to here, we're going to have a rotation of 60 degrees, and so that's going to be 4 pi thirds. And then this quadrantial angle is 270 degrees, so it's 3 pi halves. And then, of course, over here, this is 0 and 2 pi in terms of radians. Now, I did that really quickly, but if for no other reason, understand that this angle is going to be the same thing as a 30-degree angle. This angle is going to be the same as a 45-degree angle. This angle is going to be the same as a 60-degree angle. Now this is going to be important because when we're talking about these rotations, 30, 45, and 60 and iterations of those are going to be useful for us. Those in the quadrantial angles, or everything that we've done here, is really going to end up being something that you should memorize or pretty close to it. Now let's talk about the area of a sector of a circle. Sector just meaning a small portion of it. Let's remind ourselves the area of a circle, and the area of a circle is pi r squared. Now the reason I say that the area of a circle is pi r squared is because now if we want to talk about the area of a piece of the circle, then you can really think about this A that they have, this A is equal to a portion, this shaded portion. Well, how much is that shaded portion? Well, if theta is radians, then that's really theta over 2 pi. It's almost like a percentage times pi r squared. Well, then what happens, you can simplify this. Pi divided by pi is 1, and this is going to be theta r squared divided by 2. And so I claim that the area of a sector is 1/2 r squared theta. Notice that this is the exact same thing as that, 1/2 r squared times theta. And so that's what happens. Now, notice that this thing only works when theta is measured in radians. And so often enough, we have to watch out, and we're going to need to be working in radians. So let's find the area of the sector of a circle with radius 5 feet formed by an angle of 40 degrees. So if it helps us, let's draw a picture to start. I have this circle. Let's do standard position. We're going to rotate 40 degrees. So this is a 40-degree angle. And then we want to find this region, A. Well, we know that A is equal to 1/2 of theta times r squared. We know that that's the area of a sector. But let's be careful. Remember that theta has to be in radians. Well, we're given degrees, so that means we've got to convert degrees to radians. So 40 degrees multiplied by our unit conversion, that's going to be pi divided by 180 degrees. So that's going to be 2 pi ninths radians. All right, that's what we need, because remember, we have to be working in radians here. So 2 pi ninth radians. Well, then our area of the sector is 1/2 of theta r squared, where r is just the radius. Okay, this is great. The area of this sector is going to be 1/2 of 2 pi ninths times 5 squared. Now, if they asked for it in a different thing than feet, we might have to convert it, but we're fine here. 5 feet, that's going to get our units right. So that's going to be 25 pi ninths feet squared, but because we're told to round to 2 decimal places, I get that this is approximately 8.73 feet squared. And so that's the area of that shaded region. Some more definitions and applications. Well, we're going to have this thing called linear and angular speed. Well, linear speed, we know what linear speed is. That's going to be the distance traveled per unit time. Miles per hour is something we use often enough in our vehicles. For our notation, v is going to represent linear speed. S is going to represent distance, and t is going to represent time. If that's the case, then our linear speed v is equal to s divided by t, where s is distance divided by time. Similarly, we're going to talk about angular speed. Well, angular speed is really going to be defined by the amount of rotation per unit of time. And so the Greek letter omega is going to be used in general for angular speed. So that is, omega is going to be equal to theta, where theta is the amount of rotation divided by time. Now, something to note about angular speed. Just like with linear speed, you can talk about miles per hour, feet per second, meters per second, kilometers per hour. The units could change, it's still linear speed. With angular speed, same thing. It could be degrees per minute. It could be radians per hour. It could be revolutions per minute, where revolution is just a full rotation. So units come into play, and we have to consider them. Well, if you combine those linear and angular speed formulas, then what you can get is you can say that linear speed in terms of angular speed is going to be linear speed v is equal to the radius r times omega, which is the angular speed. V is equal to r omega. Now specifically, we're assuming that omega is angular speed as a radians per unit of time. And actually, we're going to say that this is necessary for this to work. And so for this formula to work out, the units of distance of v and r must be the same. Omega must be in radian per unit of time. And the units of time for v and omega must be the same. So you just have to make sure that your units match, and omega is in radians per time. So let's try a problem. Let's go ahead and write that formula down. V is equal to r omega. So a child is spinning a rock at the end of a 2-foot rope at the rate of 180 revolutions per minute. Find the linear speed of the rock when it is released. Alright, so first off, we have 2-foot rope. That's our radius. We have 180 revolutions per minute, which is technically our omega. But notice that there's a problem. It's revolutions per minute. And so we're going to have to adjust this because remember, for this formula to work, we need omega in radians per time. And so we're just going to be in radians per minute. So then what do we get? Well, if omega is 180 revolutions per minute, and I need to get rid of revolutions and put it in radians, well, 1 revolution is equal to how many radians? A full rotation is 2 pi radians. And so my conversion factor is going to be multiplied by 1 in disguise. That's going to be for every 1 revolution, there are 2 pi radians. Revolutions cancel with revolutions, and I get that this is 360 pi radians per minute. And I'm just writing radians to keep myself on track. Now we're okay. Then if I want to find the linear speed, at this point I can say v is equal to r omega, and as long as v and r are the same, but since v is not fixed, v is just going to take on the same unit as r does, which is feet, and then we're going to be in time minute. So that's just going to be radians is 2 feet times 360 pi radians per minute. Since radian is technically a unitless measure, feet is just taken on, and this gives us 720 pi feet per minute. And they didn't tell us what linear speed they wanted us to be in, they just said linear speed, and so we're good.